A van has a mass of 3,200 kilograms. The diagram shows the van just before and just after it collides with the back of the car. Before the collision, the van has a mass of 3,200 kilograms and a velocity of 5 meters per second. We're not told anything about the car other than it's stationary, so it has a velocity of 0 meters per second. Calculate the momentum of the van just before the collision. Momentum is mass times velocity, which equals 3,200 times 5. Put that into my calculator, and I get a momentum of 16,000 kilograms meters per second. So there's my answer. The collision makes the van and car join together. What is the total momentum of the van and the car just after the collision? Well, momentum is a conserved property. What that means is that momentum before the collision and the momentum after the collision will be exactly the same. So we're not given any space to do any working out here. We're not given any of these lines, for example. So we're basically being asked for a number that's either pretty obvious or it's a number that we've already calculated in the question previously. So that again is 16,000 kilograms meters per second. Complete the following sentence by drawing a ring around the correct line in the box. The momentum of the car before the collision is blank the momentum of the car after the collision. We're just talking about the car here, not both. So the momentum of the car before the collision, well, it's not moving before the collision, so it's going to be 0. And after the collision, they move off together, so it's going to be less than. A seatbelt is one of the safety features of a car. In a collision, wearing a seatbelt reduces the risk of injury. Use the words and phrases from the box to complete the following sentences. In a collision, the seatbelt stretches the time it takes for the person held by the seatbelt to lose momentum compared to the person not wearing a seatbelt. So if you're wearing a seatbelt, you will slow down more slowly. So that increases the time it takes for you to lose your momentum. The force on a person's body decreases, so there is reduced risk of injury. The car driver sees the traffic in front is not moving and brakes to stop his car. The stopping distance of the car is the thinking distance plus the braking distance. What is meant by the braking distance? That is the distance travelled whilst braking, or the distance travelled under the braking force, or the distance travelled between applying the brakes and stopping. The braking distance of the car depends on the speed of the car and the braking force. State one other factor that affects the braking distance. That could be icy or wet roads, or just road conditions. You could also say the tyres, whether they're worn or new, the road surface. So that could be a dirt road versus a concrete road versus a tarmac road. You could also have, I suppose, the gradient, how steep the road is. And you could also have the number of passengers, because the number of passengers, if there's more passengers, the car will be heavier, which will mean it'll have more momentum, which means it'll need more force to stop it. And how does the braking force needed to stop a car in a particular distance depend on the speed of the car? If you think about it, a car that's travelling at 30 miles an hour needs a certain amount of braking force to stop it in a particular distance. If we double that speed, we also need to have a much greater braking force. Figure 1 shows the distance time graph for the car in the 10 seconds before the driver applies the brakes. We've got a graph showing time in seconds on the x-axis and distance in meters on the y-axis, and you can see here it's not just a straight line. It actually curves here and then it becomes a straight line. What's the question asking us to do? Use figure 1 to calculate the maximum speed of the car was travelling at. Okay, so the maximum speed, that's going to be where the graph is the steepest. What we need to do is we need to work out the gradient of that graph. And what we're going to do is we're going to look, and from around about 6 seconds, the graph looks to be straight. Before 6 seconds, this portion is curved. After 6 seconds, it's straight. So if we follow that across, we see that's 80 meters. And then we can work that all the way to 10 seconds at 170 meters. So our change in distance is 170 minus 80, which equals 90 meters. Our change in time is 10 minus 6, which equals 4 seconds. And if we work out our velocity, which is our change in distance divided by our change in time, 90 divided by 4, which equals 22.5 meters per second. The car did not stop in time. It collided with the stationary car in front, joining the two cars together. Figure 2 shows both cars just before and just after the collision. We're given all the information we could possibly need about the cars before the collision. We're given their mass and their velocity for both of them. After the collision, we're given no information. The momentum of the two cars was conserved. What is meant by the statement, momentum is conserved? A conserved property is something that's the same before an event as it is after the event. So total momentum before equals total momentum after the collision. Calculate the velocity of the two joined cars immediately after the collision. This is a 3-mark question, so there's a couple of steps to this. So momentum before equals the mass of car 1 times the velocity of car 1 plus the mass of car 2 times the velocity of car 2, which gives us 1,500 times 8 plus 900 times 0. Well, 900 times 0 is 0, so we can ignore that. So 1,500 times 8 is 12,000 kilograms meters per second. So the momentum after will equal the mass of car 1 plus the mass of car 2. We're going to multiply all of that by the velocity after. So V after is what we're looking for. So we need to fill in the other numbers. Well, the momentum after is the same as the momentum before. So 12,000 equals the mass of the two cars, which is 1,500 plus 900 times the velocity. Let's switch this around. So we've got V on this side. 12,000 divided by 1,500 plus 900, which is 2,400. We get 5 meters per second. And that is our answer. That is our velocity. Since 1965, all cars manufactured for use in the UK must have seatbelts. It's safer for a car driver to be wearing a seatbelt compared with not wearing a seatbelt if the car is involved in a collision. Explain why. First thing is that the seatbelt stretches. Not a lot, but it does stretch a little bit. Driver slows down more slowly, reducing the force on the driver for the same change in momentum. That'll get us probably 3 of the 4 marks. A smaller force results in less serious injuries. Complete the following sentence. The momentum of a moving object has a magnitude in kilometers meters per second, and, well, momentum is a vector, so it has magnitude and it has direction. A car being driven at 9 meters per second collides with the back of a stationary lorry. The car slows down and stops in 0.20 seconds. The total mass of the car and the driver is 1,200 kilograms. Calculate the average force exerted by the lorry on the car during the collision. Show clearly how you work out your answer. First thing we need to do is we need to work out the change in momentum, because force equals change in momentum divided by time. So our change in momentum is our momentum before the collision, 1,200 times 9.0, minus, well, it's going to be the same mass, 1,200 times 0 meters per second, because it's now stationary. So this bit we can ignore, because 1,200 times 0 is 0. We're going to divide that by the time it takes to stop. Gives us 10,800 divided by 0.2 equals 54,000 newtons. Within 0.4 seconds of the car hitting the back of the lorry, the car driver's airbag inflates. The airbag deflates when it's hit by the driver's head. Use the idea of momentum to explain why the airbag reduces the risk of the driver sustaining a serious head injury. So it increases the time taken to stop. So it decreases the rate of change of momentum, and this reduces the force on the head, and that reduces injury. So now a question about a student investigation of the motion of glider on an air track. An air track is basically something that can make a frictionless surface. If you've ever played air hockey, it's kind of the same sort of idea. There's a metal track with lots of little holes in it, and we blow air through those holes and it creates a cushion of air that this glider can glide across and move very, very smoothly with no friction. The data logger and the light gates give us information on how fast the object is moving. The speed of the glider is the same at both ends of the air track. What is the tendency of objects to continue in the same speed at the same direction called? The tendency for an object to continue doing the same thing that it's doing already, unless there's a force acting on it, is called inertia. The glider has a mass of 0.14 kilograms and a velocity of 17 centimeters per second. Calculate the momentum of the glider. Okay, so we need to be a little bit careful here because we've got a 3-mark question just for working out momentum. So there's got to be a little bit more to this than just plugging the numbers into the equation, because our equation is momentum equals mass times velocity. So what does that mean? Well, our mass, 0.14 kilograms, I'm happy with that. Here it is, our velocity, 17 centimeters per second, and our answer needs to be in meters per second, or kilograms meters per second. So this centimeters is a bit problematic. So 17 centimeters per second, to work that out in meters, we need to divide by 100. So 17 centimeters per second is 0.17 meters per second. If we multiply those two together, we get an answer of 0.024 kilogram meters per second. Figure 2 shows 2 identical gliders travelling at the same speed in opposite directions. The gliders collide and stick together. Explain what happens to the momentum and to the speed of the gliders. So these identical gliders, so they're the same mass, and they're travelling at the same speed in opposite directions. What that means is that going in this direction, you have a momentum, and going in this direction, you also have a momentum. And because these are the same mass and they're travelling at the same speed, the momentums are equal. And because they're in opposite directions, that means they cancel each other out. So momentum before collision equals 0, because we have momentum minus momentum, which equals 0. Momentum is conserved, so the total momentum after collision equals 0. So the speed must be 0 meters per second after the collision. The light gate on the air track shown in figure 3 aims a beam of light at a sensor, and a data logger calculates the speed of the glider. The data logger divides the length of the card, so the length of this card here, by the time which the card takes to break the beam of light. So the beam of light goes from here to here. Figure 4 shows two vehicles on a road, and we've got a light sensor and a beam of light coming from this emitter. The beam of light and light sensor shown in figure 4 are not suitable for determining the speed of vehicles on the road. Give 2 reasons why they are not suitable and give an explanation for each reason. Here we've got 2 cars and they're both travelling in the same direction. Now, we could have more than one car passing through the beam at once. If we had these 2 cars passing through the beam, and maybe the darker coloured car was slightly further ahead, then that would mess up the measurement because the car would be longer. So more than one car passing through the beam at once means the sensor wouldn't accurately measure the time it takes one car to pass. Reason 2, cars aren't all the same length, so speed would not be able to be calculated. So if you imagine a coach goes past at 70 miles an hour and a Mini goes past at 70 miles an hour, the coach is going to take a lot longer to go past than the Mini, so it's going to appear that the Mini is going faster, when in fact it's going at the same speed.